Hi, my name is Nicolas Santamaria, and today I'm going to present our project of Group 8, Characterization, Design, and Simulation of a Centrifugal Pump by means of CFD. Now we present the agenda of the day.
First, introduction. Initially, it is very important to highlight that for the purpose of the calculations, values, parameters, and others, we use Gulich nomenclature. As we can see in this table, we have units in meters, Pascal, revolution per minute, kilograms. Additionally, as keywords for the development of our project, we have definition like cavitation, CFD, viscous flows, mesh, efficient, and wall G+.
It's important to carry out a literature review in order to understand important meanings around the development of the project, such as those present below. This is the objective of the project with the objectives of design of simulating a centrifugal pump with two specific fluids, water and oil. The design responds to ground fault specifications. This is how it is possible to carry out a review in literature, establish materials and methods, obtain results, and discuss to finally obtain conclusions. The methodology is important, and in the first step, modeling of the pump following in the algorithm Valdez et al. 2020 part of the methodology called numerical is in Excel. The 3D model of the pump part of the methodology called geometric is in Autodesk Inventor. And the pump simulation part of the methodology called simulation is in Star CCM.
Now we present some of the parameters that we got in our design in Excel for the geometry of the pump. And this is the 3D modeling that we made in AutoCAD Inventor.
Okay, this important part is the mesh consideration because it's an important part for the desarrollo or development to the project. Additional surface control was carried out on the tips of the blades so that the cells near them were smaller. The volutes so that it had larger cells because not so many relevant events occurred at the point. And on the liquid-liquid interface to remove the print layer.
Okay, for the part of the mesh independence, we made 3 different meshes. One was the reference mesh that my partner already presented. The other one is a thin mesh with less 30% base size, and the other one is a thick mesh with a base size augmented 30%. Here are the parameters that we are going to take out on the report of each of the meshes. And now we present the results of all of the reports that we made from each of the meshes. As we can see, the thick mesh, that the one that says 30%, is the one with the best results. So we can see in these tables, in these graphics, that in efficiency, in head, and in total solder CPU time, the thick measure was the best and got the best results that we can have. Is this for the reason that we decided to use this thick mesh for the simulations?
For physical models, we have a boundary initial conditions. We have 2 liquids, water and mineral oil, like conditions like you can see. We have to do 5 simulation in the shut-off point, the midpoint, the manufacturer bit, the 3D library, and finally the bit of design. Regarding the physical models of working with liquids that had a constant solid density, for which it was found as an incompressible fluid due to the fact that turbulence is present, the epsilon is used. Additionally, it is speaking of a segregated fluid and is found in a stationary state. And we have to use like in 3-dimensional.
Okay, now, so we made the graphics that we took from example from the Valdez et al., in which we had the experimental efficiency versus CFD efficiency, as we can see in the graphic from the left, and in the graphic from the right, we can see experimental head from CFD head. We can see that many of our results got into a range of from 10% to less than 10% of the expected.
Operation curve. As it can be seen in the curves of operation of the centrifugal pump, the behavior of the water simulation and the oil are similar to the one presented by the maker. However, this is a small difference between the oil curve and the water curves, since the first one has a proportionally lower values than the water simulation, and this is due to the own properties of the fluid. In other matters, it is important to specify that just 5 simulations for each substance were made. This is the reason why it can exist in the design a range of error related to the lack of data. Nevertheless, these few differences observed in the curve can be due to losses caused by recirculation or stalling near the end of the blade tips. Power and efficiency curve. These are the power rate and efficiency curves versus the flow rate. As observed with the increase of the flow rate, there is also an increment in the power rate of the substance as well as the higher efficiency in a flow rate. Of the higher efficiency in the flow rate of 140 flow rate for the water simulation and 180 for the oil simulation. Moreover, as mentioned before, these behaviors are similar to the maker one. For the velocity profile from the simulation made by the program star were obtained a series of velocity profile for the water and the mineral oil. In this case of the water exists a higher velocity in the rotating zone and also an increment of this one with the increment of a flow rate. Although this velocity decreased in the outside of the zone and proceeds to become constant. The velocity profile for the mineral oil happens something similar to the one in the water simulation. In this velocity increase in the rotating zone, however, it is proportionally lower in compared to the water.
Okay. Sorry.
On the other hand, the pressure profiles for the simulation for the two substances describe the decrease on the absolute pressure with the increment of the flow rate. And also the pressure profile for the mineral oil present a lower values than the water simulation with the increase of the flow rate.
Now we can see a simulation 5 for water and oil and from left to right. In the first one, we find the comparison of the results of the Y plus, and we show that this is reader for water, and this is why due to characteristics such as the viscosity makes the Reynolds number and the meshing process differ significantly. So it is correct that is be higher for water. In this slide, we can find the cavitation that the simulation will present, and we can show that it is to a greater extent at the tip of the blades where our pump could present problems due to the same problem. Now, we'll be able to observe the behavioral animation of water and oil.
Finally, for the conclusions, the CFD simulation for a centrifugal pump allow us to analyze its performance against two different fluids, water and mineral oil, where it was observed that the total head and the efficiency decrease at higher flow rates in some cases. Also, in terms of quality plus, we have a higher value in water than in mineral oil, and this is because the viscosity of water is higher. Similarly, it was observed that the cavitation phenomenon occurs at the tips in the blades. Additionally, it was observed how the efficiency and the total head of the pumps depend on the properties of the substance, which works an example of density of viscosity. Finally, given that the wall G plus were obtained with a value less than 5, it can be said that we are in the subviscous layer in the machine is called refined. And the last one is reference. Thank you.
Thank you.